Now in this video we want to look at adjusted r squared versus r squared. So r squared from chapter 5, r squared is just the variance due to the model. Okay, so the y equal beta x plus alpha, so that straight line model, there's going to be some variance in the y values simply because if you have a slope, right, I've got a slope, even if the data go right along that line, well, if you look at the y values are doing that, well, they will have a variance to them, right? And that's due to that straight line. And then divided by the total variance. So if they completely fit exactly on the straight line, then we would see that the variance due to the model and the total variance would have to be the same thing because all these dots are right along that line. But if I have dots off the line, but that is the best trend, well, then some of that variance that we'll see is coming from somewhere else. Now that somewhere else might truly still be the basic model in that, again, remember from chapter 5, they're saying our basic model is that the center at each x value, the center of the y's is along that line, but they have a normal distribution of error then for any given x. And so, we would still expect to see some total variance, but in that way, and remember, variance is just the square of the standard deviation. So r squared is just really a percentage, you can think of it that way, of how much of the variance in the data is explained by the line we had picked. And so, r squared of 0.9 is really nice. I mean, that means 90% of the variance was explained. R squared of 0.1, only 10%. So, that's not so great. It doesn't mean it's not the best model. It just means that maybe the data have a lot of variance to them besides just the model, the straight line model itself. So that's r squared. And so generally speaking, we would like to see r squared be big. Adjusted r squared takes into account the number of variables. And we'll see why this matters. Now our definition of how we calculate it is if I want my adjusted r squared, what I'm going to do is first take 1 minus the r squared. So I'm going to space over here a little bit. 1 minus the r squared. Now what that gives us is then the variance that's not due to the model over the total variance. Okay, so it gives us that. And then we multiply that by n minus 1 over n minus k minus 1. Now k is the number of variables, so again n is cases, k is variables. And so you see what happens is as k gets bigger, okay, as k gets bigger, n minus k, now we've got, or n minus 1 minus k, that gets smaller. Okay, if I have some number that's fixed, the n, and I subtract off another number that's getting bigger, that difference gets smaller, right? 10 minus 2 is 8, but 10 minus 6 is 4. And so this number on the bottom gets smaller and smaller and smaller, which makes the fraction bigger. And so we multiply this 1 minus r squared by a bigger number. And then, so that makes that bigger, but then we do 1 minus all of that, which makes it a bit smaller. So what we have is that the adjusted r squared is always going to be a little less than the r squared, or possibly a lot less. But what we see is this k being there is we get extra penalized by more variables. And if n is really big, it doesn't really matter too much, you know. So if n is like 10,000 and we add another variable, we're not going to really see a difference in our adjusted r squared, usually. Not much of a difference. Whereas if n is small, like maybe just 10 data points, then seeing differences in the number of variables actually will really impact that adjusted r squared. So we're going to use adjusted r squared to kind of determine how well our model is doing. Now, and what we want to look at is, you know, why we care about this number of variables. And we want to talk about this thing called the bias variance trade-off. Okay, and what that means is that if I have fewer variables, typically what happens is the model is less biased, but has more variance. Okay, in other words, it doesn't explain the given data as well. More variables, as I add more variables, what happens is the model is more biased, but has less variance with the given data. Now, to see a picture of that, I'm not actually going to use more variables. In a sense, you know, we'll see later that in a sense I am using more variables, but just to give us an idea here. So I'm going to just take 3 data points so it's real easy to see what's going on and all that. And so suppose I have those 3 data points. Then if I fit my straight line, maybe it does something like that. And this would be my y equals beta x plus alpha. Well, you see that that has some variance here that's not part of the model. So I'm just using the one variable x, and so I have a little bit of variance in my answer here as far as what the model doesn't explain. On the other hand, what I know is if instead of using this straight line function, if I used a parabola, I could actually hit those points exactly. And so this would be a model y equals beta 2 x squared plus beta 1 x plus alpha. And so what we see here is this model is exact. It's reduced that variance to 0. Okay, so definitely less variance. But here's the problem is I fit these data with this model, but probably I want to think of it as a predicting sort of model. Well, I'm going to get more data. And as more data gets filled in particular, suppose it really is kind of a linear relationship, you know, as I fill in more data, what we see is this model over here has less bias. It assumes a bit less about the data, and therefore when we start filling in with more data, it's probably going to do better. I say probably because, well, it's much more complicated than just looking at 3 data points usually. But this is an illustration. And so here, by using, in a way, more variables, you know, I could say, well, I've got the variable x, and then I've got the variable z, which is the same thing as x squared. Whoops. So I've kind of introduced, in a way, more variables. And I got this beautiful model. It goes right through the data, but the problem is, if I start adding that other data, like I did over there, what you see is that what used to look like a beautiful model doesn't look very good anymore. And that's because, in essence, I ran into this problem of overfitting. And overfitting is when you use way too many variables. You know, here I did an exaggeration of just adding one more variable was a really bad idea. It may not have been, but generally speaking, this idea of overfitting really is a problem. Because what we know is as you increase variables, and this is another reason for using adjusted R squared, is that if I call this R squared of, say, one variable, what I know is it will be less than or equal to R squared of, say, two variables. And if I kept adding variables, and the amazing thing is, it doesn't matter what those variables are, whether they really do matter as far as the response variable. But as I add more and more explanatory variables, my R squared gets bigger, which would say, oh, that's a good thing, R squared gets bigger. And you can kind of see that in this parabola example, in that as I add, if I have dots like this, you know, as I add powers of x, which are a lot like adding variables, I can always fit my data perfectly if I use enough of them. And so I can just keep making R squared bigger and bigger and bigger. But it could be that you could have something like this, the adjusted R squared of one variable actually can be bigger. It doesn't have to be. Okay, so I'm going to put a question mark under that. But it can be bigger than the adjusted R squared of two variables because of that k that we put in there. And so that's why the adjusted R squared is a bit better number to use than just the R squared. And so in our project and and when we work with these things, we're going to look at adjusted R squared. Because what we really want to do is find exactly the right number of variables to use, and we don't want to use variables that don't really help and they just hinder. And so we're going to, in this linear regression with multiple explanatory variables, we're going to kind of go back and forth between the modeling aspect of, well, are we looking at the right set of variables for our statistical test? You know, that's the modeling aspect, and then we'll also look at our statistical test of our betas and look at the p-values that go with those slopes. Okay, but that is this difference of R squared and adjusted R squared. Is we use our adjusted R squared to help us not overfit. You know, it's always nice when we do more variables and we look at it and we go, oh wow, the model fit great, but the problem is it's more biased. And so we want to, you know, like we had here, and so we don't want to do that. Okay, and again, there's our definition of adjusted R squared. We have to take our R squared, subtract it from 1, multiply by this fudge factor involving the number of variables, and then subtract that from 1. Okay, so oops. So that is this idea of adjusted R squared.